Alright, so we're going to start with chapter 3, which is going to be all the shortcut rules for derivatives. We've talked about how to find the derivative the long way using the definition, which translates to the limit of the difference quotient, which, by the way, is nothing more than the limit of the slope of the secant line between 2 points. But we're going to actually get into shortcuts this time with derivatives. Because you can't always do those well, you can, but it makes it a lot easier when we've got those shortcuts, doesn't it? First of all, just to review, here is our definition of the derivative, and if we have an a there and there, then it's the derivative of f at a. If we have an x there and there, then this is just the derivative of f, and we can evaluate it whatever we want to plug in for x. But that is the definition. Anytime they talk about doing the definition or the limit process, you have to use this method to find it. So we can also write f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So f prime, that's notation for a derivative. And that's exactly how it is read. The derivative of f with respect to x is our limit. Now, there are many ways that we can write the derivative of y equals f of x. Notations are different here and there and everywhere. There were two really important, I guess you could say, fathers of calculus, and both of them had different notations. So we actually have, that's why we have multiple notations for it. Let's look at some notation. The first one is our prime notation, and this is just simply saying f prime of x is the way that's read, and that's going to be the first derivative. So we can read it as f prime of x, f prime x, or the derivative of f with respect to x. Now our second notation is just y prime in place of f. Instead of using function notation, we use y, and that will be read y prime, or the derivative of y. And dy dx here, this is another type of notation, but it's more specific because it's telling what you're taking the derivative of and what you're taking the derivative with respect to. This x down here tells you that you're taking the derivative with respect to x. That's important because you can actually take the derivative of a function in multiple different ways with respect to multiple different variables. We're primarily going to deal with one variable at a time, but later on in Cal 3, if you take Cal 3, you're going to have what's called multivariable calculus, where you may take a function and take its derivative with respect to x, and then y, and then z. You never know. But this is read dy dx. And it is the derivative of y with respect to x. All right, and the same thing with function we can do with function and with function notation, and this is just df dx. That's the derivative of f of x with respect to x. Now, in both of these, and actually all four of these right here, we're kind of using this notation as a noun. This is a derivative, this is a derivative, this is a derivative, this is a derivative. The next one is a little different. We're doing d dx of f of x. Well, this part, the d dx part, is more of a verb. It's an action. And this is what we're taking the derivative of. But this is read d dx of f of x. It's also the derivative of f of x with respect to x. So there are some of the notations that we're going to use and that you need to be responsible for and understand. They'll make a little more sense as we get through more. All right, some notes here. dx does not mean d times x. Same way, dy does not mean d times y. dy dx does not mean dy divided by dx, except when it's convenient to think of it as division. And we will talk about times when that's true. But not right now. We're not ready for it. But just understand, dy dx is not dy divided by dx. And the same thing with df dx. And ddx of f of x does not mean ddx times f of x. That's an operation, remember. It's something that you're doing. It's more of a function than it is an operation or a number. All right, so let's look at this. We've got a function here, y equals f of x. And if we were to go through and try to draw the derivative graph of f of x, what we want to do is we want to look at the intervals we're doing here and what the slope is over those intervals. So the derivative is nothing more than the slope of the original function. So that means when we go down here to graph the derivative function, over the interval from 0 to 1, we want our derivative graph value to be whatever this slope is, which by the way is 2 divided by 1, or 2. So over the interval from 0 to 1, we have a value of 2. It's constant for that whole direction because the slope is constant over that line. Now, at this point right here, we're going to talk more about this later, but notice that that thing right there has an open dot at 1. The reason why is because, well, we can't really identify what that slope is. We'll talk more about that later. And then over the interval from 1 to 4, we could find the slope of this. It goes up 1 unit, but it goes over 1, 2, 3, so that's 1/3. So over the interval from 1 to 4, we have a value of 1/3. Now, real quick, let me go back. The derivative is defined at the endpoint of a function on a closed interval. It is not, it's kind of hard to explain, but it's defined here because there's nothing over here to contradict the slope that we have all the way to the point. Whereas right here, notice we have an open dot. Well, these two fight for which one has the slope rights to that point. That's why we have an open dot on both of these two. Open dot there, open dot there. This point right here at x equals 1, we don't have a derivative value for it. All right, and then over the interval from 4 to 6, it's constant, so the slope is 0. There's that. And then from 6 to 9, we have a slope where we're going down 3 and over 1, 2, 3. So we have a slope of -1. So from 6 to 9, we have a slope of -1. And once again, at this endpoint, there's nothing over here to this side of 9 to battle with that. So we give that endpoint to the derivative on this side. So that's all we're looking at. Whatever the slope of the original function is what the y value is for the graph of the derivative. All right, so let's find the derivative of y equals x squared minus 3. Well, we could do it this way and go through the process. Don't write all this down in your notes. You don't need it. We've done plenty of work with this. And you're going to end up getting the derivative is 2x. Y prime equals 2x. And we've already talked about it a little bit. Some of you guys have had physics. You know the rule we're looking at here. But let's go ahead and expand this a little bit and talk about it. So right here we know x squared minus 3 is the red. 2x is the blue. What I want you to look at is I want you to look at any point on the red curve. Pick a point. Let's say here at 1. And get an idea of what you think the slope may be there. That's not exactly 1. Let's put it right there. And we can get, let me get a line. That's not a line. Let me get a nice straight line here. We're going to move that thing over to where it's tangent. Okay, maybe I'm not. I thought there was a way I could turn this. Okay, anyway, so let's turn it that way. All right, so that looks fairly tangent to that right there. Now, here's the thing. We could estimate what that value of that slope is, and we're going to. But an easier way to do this, let me go ahead and draw another line over here, but this one's going to be straight up and down. It's going to be vertical. All right, and I'm going to move it over to where x equals 1. So my point's still a little out of the way there. It's still a little off. Let's move that line out of the way for just a second, and I'm going to move this point. No. Move this point down. All right, so we'll say right there. Then we can bring the point back in here, the line. I might have to adjust it a little more. All right, so there it is. But what we could also do is we can follow this line up right here and look at what the value is right here. Because what do we know? We know that y prime is our derivative. Well, our derivative is also the slope of this red line. So if I want to know what the slope of the red line is right here, or red curve is right here, I can just look at the blue line, find out what its y value is, and the slope there should be 2. Now, I'm looking fairly tangent here, so let's go ahead and evaluate and see if this is really a slope of 2. So I'm going to move it up here. I'm going to put one endpoint right there on -1 and see about where this ends up. Now, it's not exact, of course, because I wasn't exactly, but you can see there that it does go up over, it does go up 2 and over 1, so that is approximately a slope of 2. So what we can do is any point on this graph we want to, we can find what the slope is. So if I were to take this and move it on across, what is the y value on my blue line right there? Well, it's 0. And what do I know down here on my red curve? I have a tangent line that is 0 because that's a minimum value. I'm going to have a horizontal tangent there. And if I go on over here to -1, well, it just so happens that those two lines cross there. That's not something that you're looking for or anything. But what do we know? Well, we know that if we follow the blue line, it has a slope of -2. And when I say it, I'm talking about that red curve. The red curve will have a slope of the tangent line of -2 there. And guess what? It will also have a value of -2 there. And what do we know is going to happen as we move further and further over this way? Well, over here, my curve is going to do what? It's going to get steeper and steeper and steeper in the negative direction because my slope is getting larger and larger and larger negative. Over here, same thing's happening except it's going to the positive direction. Notice my slope here, increasing, increasing. Notice here, my blue line value of y is increasing, increasing. All right, a function is differentiable if it has a derivative everywhere in its domain. Differentiable means that you can take its derivative. So it's differentiable only if it has a derivative everywhere in the domain or in the interval that you're talking about. It must be continuous and smooth. Functions on closed intervals must have one-sided derivatives defined at the endpoints to be called differentiable. That was similar to what we were looking at just a second ago, where the endpoints were filled in but the points in the middle were not. That's what we're talking about, the one-sided derivatives. All right, that's the beginning of it. Just kind of get an idea of that information, and we will go from there. We'll add to it.